Welcome to our 12th lecture in dynamics. Because we have about somewhere in the area of 40 lectures in this class, maybe a little bit fewer. We're somewhere between a fourth and a third of the way done with the material, which is really amazing to think about. In lectures 10 and 11, we covered sections 13.1 and 13.2, dealing with work, energy, and the conservation of energy principle. So today I'm going to work a problem that's sort of an example from each of those sections so that you'll have those as you start to do your homework. Now if you look at our Moodle page, this is the lecture that I'm going to do today. So as you can see, the homework for chapter 13, so far I have 2 homework sets. And since we're doing a problem-solving session today, we will not have another homework set. This is it for the weekend. So I will do a problem from the first, similar to the first set. I'll do problem 13.18, and I'll do a problem from the second set, which I chose 1385. All right. So these problems are not identical to the homework, but they're very similar in that they bring in all of those ideas about using work energy and the conservation of energy principle. So let's get started. There we go. All right, so on problem 1318, one of my favorites, a train problem. And I think you're doing 1317, which is also a train problem. So this one is remarkably similar to the homework problem that you will have. We say a subway train shown is traveling at a speed of 30 miles per hour when the brakes are fully applied to the wheels of car C, causing it to slide on the track, but are not applied to the wheels of B or C. Knowing that the coefficient of kinetic friction is 0.35 between the wheels and the track, determine the distance required to bring the train to a stop and the force in each coupling. All right, so here's what we have. We have car A, coupling, car B, coupling, and car C. The train is moving in this direction, and our speed is 30 miles per hour, which we're probably going to want to change into feet per second. Maybe not, but I'm thinking it's maybe a safe bet. And we're told that the coefficient of kinetic friction is 0.35, and that we are just applying that to the brakes on car A. The force on A of friction. Okay. And the kinetic coefficient is 0.35. All right, so here's sort of our facts. We're also told that car A weighs 40 tons, and B is 50, and 40. Okay, and even though we don't have friction, we still have wheels, right? All right, so the first thing that we would do, we're going to have to find, let's see what we're looking for here, 17, 18, the distance and the force in each coupling. So the distance that we're going to travel in order to get to the velocity of 0 or the speed of 0, and then we want to get the force in the coupling between A and B, force in the coupling between B and C. All right. So to do the distance traveled, we're going to be able to look at the train in its entirety, but in order to get those forces in the coupling, we're then going to have to break it down into different cars and decide what's going on. All right, so the first thing is, let's go ahead and change some units. I don't know if we're actually going to have to, but it's always a safe bet. Miles per hour, tons, not good units. So they're not base units, let's put it that way. If we have 30 miles per hour, if we wish to change that into feet per second, we know that there's 1 mile per 5,280 feet, and we know that 1 hour is 3,600 seconds. All right, so if we change that into feet per second. We take 30, multiply it by 5,280, and divide that by 3,600. And we get our speed as 44 feet per second. Okay, now what about a ton? Well, 1 ton is 2,000 pounds, or we could say it's equal to 2 kilopounds, which a kip is 1,000 pounds. So 40 tons times 1 ton per 2 kips is 80 kips. So this train has a weight of 80 kips. This train car, excuse me, this has 80 kips. And this has 50 times 2, which is 100 kips. All right. So far, so good. Well, if we think about this in terms of the work done by friction, which is a nice way to handle that non-conservative force, we can use you can use the work energy principle and say that the kinetic energy at time 1 plus the work done by friction from 1 to 2 equals the kinetic energy at time 2. Okay? This is 0 because we want that car to come to a stop. Our initial kinetic energy is 1/2 times mass times the velocity initial squared, and the work done by friction is going to be the force of friction times the distance, which I'm calling x sub 0, or xv sub 0 equals 0. All right, now the only thing we need to think about in terms of analysis is what is the force of friction? Well, the first answer is that the brakes are only being applied at A. So intuitively it makes sense that if we applied the brakes on all 3 cars, we would have more frictional force, right? So we're going to be taking into account only the frictional force of the car at A, which is going to be, we know that force of friction on A is mu times the normal force. And since this is on a level surface, and there's, we can say that that's going to equal to mu k times essentially the weight of the first car. Right? So if we think about it in that way, we could say it's equal to 0.35, which is that coefficient of kinetic friction, times the weight, which is 80 kips. And if we take 80 times 0.35, we get 28 kips. All right. Now, when we think about taking this and putting it into this equation, the first thing we need to think about is we can call this direction negative and this direction positive, or the other way around. But the really important point is that frictional force always opposes motion. So one of them has to be negative of the other. And it's more common to think about friction if you're doing energy, if you're not doing a strict vector analysis. It's more common to think about friction as being negative to the direction. All right, so here we're not talking about the mass of just the one car. We're talking about the mass of all 3 cars, aren't we? So we would have 40 plus 50 plus 40 again for the 3 cars. But then we need to change that into some other set of units. If we call this kips, and we know that the acceleration of gravity is 32.2 feet per second squared, we're going to get some kind of an odd unit, but I think everything's going to come out in the end. Okay, so I didn't leave myself enough room. So we have 1/2 mass times the velocity, 44 feet per second, quantity squared, plus the force of friction, 28 kips. Oh, I'm sorry. After my whole big diatribe I wrote down as positive. It's actually negative, isn't it? Times that distance, which is what I'm interested in finding. How far is it going to be before it stops? Equals 0. All right. Now, if you think about this, I have kips over here, and I have kips here. I have feet per second squared, and I have feet squared per second squared. So here, I'm going to be left with just a foot. Everything else cancels out, times a kip. So over here, this term is also going to have a force, a kip times a foot. Yes?
I think the masses were 80.
Did I do that? I did that, didn't I? So you got to watch me every minute. 80, 100, 80. How's that? Okay, thank you very much. Yeah, and I've told you this before, and those of you that have had me in class know, whenever I do that, it's total full-on accident. So please do correct me because I just picked up the wrong number. I went to tons instead. All right, so if I do that, though, I have kips and kips. I'll go ahead and just work out the units a little bit here. If I take 100 plus 160, that's 260 kips. Then that's over 2 times 32.2, and then 44 squared in the top. All right, and then my units here, I have kips times feet. Just kips times feet, because I have feet squared, only feet, but second squared cancels second squared. And that's going to equal 28 kips times that x distance. When I bring it over to the other side, it becomes a positive. So if I do the math over here, 260 times 44 squared. I meant to hit equal. 260 times 44 squared divided by 2 and divided again by 32.2, and this term comes out to be 781.615 in units of kip feet. And if I divide that by 28 kips, I get my stopping distance, and the kips cancel, so my stopping distance will be in feet. So I take 781.615 divided by 28, and the answer is, hang on, I think I missed a decimal place here. Let me try this again. 260 kips, 28 kips. 260 times 44 times 44 divided by 2 divided again by 32.2. Yeah, this is 7816. I like that. Okay, so I moved my decimal place over incorrectly. Divide that by 28, and that means that my stopping distance is 279.15 feet. When I originally did that, I came out with a stopping distance of 27 feet, and I was like, no train that heavy is going to stop in 27 feet. So there you go. 279 seems more likely. All right. Now, to do the force in the coupling, we're going to have to separate out the car and look at what's going on with each car. All right. So let's take a look at car A. Now we know something about how it slows down. We know that there is a force of friction pushing it this way. And we also know that there is something going on in the coupling. Now, the coupling can either be in tension or compression. And if you set this incorrectly, it'll come out in the math. But is it going to be in tension or is it going to be in compression? In other words, if A slows down, are the cars going to tend to push up against it? Yes. So my feeling is that it's going to be in compression. In other words, that the force of the coupling between A and B is going to be pushing in this way. That would make sense to me. All right, so we have our velocity initial, which is the 44 feet per second, and we have the weight of the car, which is 80 kips. All right, and we still have wheels on the car. All right, so there we go. So if we think about it that way, we can also think about the initial kinetic energy minus this work done. But now as far as the work done goes, we have two different forces, don't we? So in other words, we can still set up the same type of an equation where we can say the kinetic energy at time 1 plus the work, let's say, done by the frictional force from state 1 to state 2, plus the work done by the force in the coupling from 1 to 2 is equal to 0, because we're getting that to stop, right? All right, so this is 1/2 times the mass times the velocity initial squared. The work done by friction, see, I guess I would probably call that, negative work, even though the direction is to the right. But once again, just like in the original problem, this is opposing the motion. This is actually pushing the car in the same direction as the motion, isn't it? Those cars behind it, without the brakes applied, are pushing it. So I would call this negative mu k times n times the distance that it's going to be required to stop, plus the force in the coupling between A and B times that same distance is equal to 0. All right, now if I keep everything in kips, I should be fine. So here, once again, we have 80, I shouldn't say once again because we had a different mass last time, 80 divided by 32.2, so that's my, it would be kiloslugs is what that would amount to be, 2.48 times 44 squared divided by 2. So my kinetic energy in those units is 2404.97. Let's keep my units kips. This is feet per second squared, so it's kip feet. There we go. Minus 0.35 times the normal force, and once again, that is an 80 kilopound train car, times the distance, which we determined to be 279 feet. So we're still good, kip feet, plus the force in the coupling between A and B, times that same distance, 279 feet, equals 0. So if I look at my units here, I have kip, feet. So that means that the force in this coupling is going to come out in kips, which is a good unit for force. All right, so to solve for that, I'm going to bring everything over to the other side of the equation, or I could bring this over. But I think I'll go ahead and say the force in the coupling between A and B times 279 feet equals 0.35 times 80 times 279. That would be in kip feet, minus 2404.97 kip feet. Okay, so then I get the force in AB is going to be equal to this, 0.35 times 80 times 279. That's 7,812 minus 2404.9, which I'm just going to call 2405. So that is a positive 5407 divided by the 279 feet, And that'll give me an answer in kips of 19.4 kips is equal to the force in the coupling between A and B. Okay, and the fact that it's positive indicates that I have chosen my direction correctly. But that wasn't chosen mathematically. That was just chosen by thinking about what a train car does if it's, or you know, if you've ever pulled a trailer without brakes. Yeah, that's pretty much what's going on here. All right, now for the second part, just in the interest of time, I'm going to set up what goes on. I want to find the coupling between B and C. And so I could set up B or I could set up C. It doesn't matter. C looks a little easier to me, right? So if I look at car C to find, now I want to find the force in the coupling between B and C. All right, so if I just look at the car C, now like I said, I could look at B, but then I'm going to have to take into account the force in the coupling here and the force in the coupling here. And I know that, but it's just one more piece of the puzzle. So if we do C, we can just talk about the coupling. All right, now the first thing is, if we think about, we don't really have any friction, right? We have the weight of the car, we have the velocity, which is moving in this direction, and then the final velocity, which is 0. The only thing we have operating on this car is the force in the coupling between B and C. And the question is, thinking about being in car C, is that coupling going to be in compression or is it going to be in tension? Is it being pulled ahead or is it being stopped? Absolutely. So otherwise it would be a very bad braking operation. That's kind of the whole point of putting on your brakes, right? So once again, we have this force of the coupling. Now we have mu, we don't have mu k, I'm sorry. We have the force in the coupling times the distance, which we know. It's going this way. And then all we have is a kinetic energy initial and a 0 kinetic energy final. So we can solve for that pretty quickly. All right? So let's put and solve. Okay? Well, like I think I had mentioned this earlier, train problems are very classical dynamics problems, and those couplings, it's sort of like the first time when you start looking at an internal force in a larger system where you have to break it down not only as the whole train or the whole system, but as the individual parts. It also shows you why couplings on trains, the actual mechanism, are pretty sturdy. And if you've ever had the pleasure of being in a train yard, when they hit against each other, they make a very, very loud noise. There's a lot of force that are taken up, and they're real stout if you look at them. They're just like big, big honking trailer hitches. So there we go. All right, the next problem I wanted to look at is in section, I'll put this up on the podium PC, for problem set 2. I asked you to do 13.86, which is an orbital problem. And so I would like to do 13.85, which 13.85 is related pretty quickly, also uses the principle of conservation of energy without really having any work involved, just potential and kinetic in a application of space mechanics. Okay, so 13.85 says determine the kinetic energy per unit mass. So we're looking at, to use their symbol, T per m, right? That a missile must have after being fired from the surface of the Earth if it is to reach an infinite distance from the Earth. All right, what is the initial velocity, which is called the escape velocity? And give your answers in SI units and show that the answer to part B is independent of the firing angle. Isn't that interesting? All right, well, basically, what's holding it in orbit? The thing that would hold it in orbit if it were not to escape would be the force of gravity, right? Which, okay, yes, I do have that flashed up there. G m over r squared. All right? So if we just look at this piece of it, as we're just talking about a missile, okay, we can say that G times r squared is equal to G times m. And the reason that we can do that is because we know the value of little g. We also know r, which is r is just, since we're on the surface of the Earth, the radius of the Earth. So what we can really do is pretty quickly calculate what our this initial term, which is related to the escape velocity, or related to the properties of the Earth. So, in metric units, we can say 9.81 meters per second squared times the radius of the Earth, which is in meters. I don't think there shows no problem there. Radius of the Earth in meters is
6,370.
Where'd you get that number?
Just on the next page, there's a drawing.
Oh, see, that would be so nice if I went to the next page, wouldn't it? 6,370 kilometers, right? All right. So if we take a look at 6,370 kilometers, that would be 6.37 times 10 to the 6 meters, right? Because it's 6.3 times 10 to the third kilometers. So if I take 9.81 meters per second squared and multiply it by this number in meters, I would come out, it's the number squared, excuse me. There we go. So let's go ahead. So we have 6.37 squared times 9.81, and then 10 to the 6 squared is 10 to the 12th. So I get equals 398 times 10 to the 12th. And my units, if I have meters times meters squared, it's going to be meters to the third over second squared. Okay, so that's a constant that we can think about using on Earth. All right, now if we think about what we're talking about, we're talking then about something going on the surface of the Earth when we have the missile on the surface of the Earth. And then we want position 2 to be something different than that, which is going to be escape, right? So if we say then that on the conservation of energy tells us that the kinetic energy at position 1 plus the potential energy at position 1 is going to equal the kinetic energy at position 2 plus the potential energy at position 2. All right, this is almost always that value. On Earth, we're going to have some sort of a kinetic energy term, a potential energy term, which is just that G m over r. Okay, because if we take this and we say this is a force, remember force times distance is equal to an energy term. So we take G m over r squared times r, and we just get this type of a term. Okay, then we want that to equal 1/2 mv at whatever that escape is, plus the same thing at this different radius. So let's just call that 1 and 2. All right. So what we're really getting at is, what do we want this R2 to be? Well, we want it to be infinity, essentially, right? We're saying we want it to go on just forever. So if R2 is equal to infinity, that means that GMM over R2 is essentially going to be equal to 0, isn't it? All right. So that tells us then that if we take 1/2 mv1 squared plus GMM over R sub 1, I'm trying to think about this. Do I like that sign convention?
So is the R supposed
I like it okay. No, because remember, it's energy. So you have to multiply the force times a distance. And so that distance is actually, in this case, infinity. But on this, you're multiplying you're multiplying R, or you're taking R and dividing it by R squared. So you're losing that R term to go from force to energy. Does that make sense?
Sure.
Okay, I'll do it again. So here we go. Force times distance equals potential energy. So in the case of orbital mechanics, this is GMM over R squared, and the distance initially is R. So when we cancel this against this, we get V initial, I should make that preference, is GMM over R. Alrighty, no, excellent question. All right, so when we think about this then, we have this kinetic energy, and we have a potential energy term. And then we're going to have that final, this one right here, the initial. See, I don't like the way this is laying out. I want to take a look. I want to put it back in these terms again. So, because what I really want is a kinetic energy per unit mass. So I can say that all of this is true. This is my second potential energy. So that goes to 0. It's not really the potential energy, it's just the term because this R2 is infinity. Okay? So I could say then that T1 plus V1 equals T2. But since I'm looking for potential energy per unit mass, and the mass of the rocket is not going to change, I could just rewrite that equation to look like this. So I'm just taking kinetic, because this is what I'm looking for ultimately, is what my kinetic energy per unit mass has to look like. All right. That leads me to the fact that this value on the surface of the Earth is actually a negative. So we get T1 over M equals T2 over M plus V1 over M. That's what I'm looking for right there. All right, so when we break it up that way, we can then say that, see, I keep on wanting to leave that other term in there. I don't know, anyway, I won't. But basically then, we can say T2 over M, got that, got this. I know that my T2, why is my T, let me think about this. This is a little bit troubling to me. I have to think about this for a minute, because it seems to me what am I going to do with this term? See, that really bothers me. I'm almost thinking I'm going to discontinue working this problem because I really don't like that concordance very well. I mean, mathematically, it's okay. Let me just do this a different way for a second. All right. So if we start with this, T1, I'll try this one more time. If I don't like it, I'm going to quit because I don't want to put something inaccurate up here, something that bothers me, is equal to T2 plus V2. That is clearly the case. 1/2 mv initial squared minus gmm over r1, being the radius of the Earth, equals 1/2 mv final squared over 2, well, 1/2 mvf, let's just leave it like that, plus gmm over r2, whatever r2 is. All right, so then what we really have to think about here is what are we doing with these two terms? Okay, so I'm going to say then T1, since this is a negative, put that right here, is equal to T2 plus V1 plus V2. All right, so this, I'm just going to leave those in this form. This is equal to gmm over r of the Earth. And this is going to be gmm over infinity. All right, now if I take each one of these then, at this point, and I divide it by mass, mass and mass, this goes away and this goes away. And I end up with T1 over m equals T2 over m plus gm capital M, which is the mass of the Earth, over r. Oh, no, see, that's what I don't like. That's where I come up with this. Okay. I know that gm can actually be expressed as gr squared. I don't like this. I do not like this substitution. It kind of bugs me. All right. Yeah, I'm sorry. I'm going to discontinue this problem. I don't even like it, so I'm going to let that one go. I'll have to work another problem, and I'm going to do it after class because we only have 10 minutes left. But I thought this problem was going to go somewhere else, and I don't like the direction it took, so I should have looked at it more thoroughly before I came to class. So I apologize for that. But what I'll do is, when I post this video, I'll ask you to just watch the first one, so that when we start working, I'll put a note that when we start this problem to discontinue the video at that point. When I get it up into YouTube, I may be able to edit it out, but if I'm not, I'll at least make a notation of that, and then I'll work a second problem for you on the homework so that we have a better one in terms of describing that situation. Yes?
Is there a way that you could just, like, instead of plugging in infinity,
yes,
just plug in a number that's like
huge?
Yeah, big
yes.
enough that gravity doesn't affect it.
Yes.
And then with that, like, solve your...
Yeah, and that's a very, very clever thing, because what ends up happening is if you look at this, I'm comfortable right to here, okay? Now, the piece that bothers me is gm over r. If I go back to this, I could say that that is equal to gr. I'm going to go ahead and finish it. I can see it already. G times this over r, right? So that means that this will cancel this. So when I go back to this equation, I can do this substitution, and then what I would get for my final working form of the equation would be T1 over m is equal to T2 over M plus little g times R. Okay, I'm satisfied with this. There you go. So I cut it all out. Everything's going to be fine. So what happens at that point then is we can think about what is going on with the kinetic energy once it escapes. Well, the escape condition is that we no longer have a condition of kinetic energy because we're not subjected to the Earth condition. Or if we want to look at that, we're not subjected to kinetic energy with respect to the Earth because we've broken out of orbit. So we can say 1/2 mv escape squared, that would be the kinetic energy on escape, is going to have to equal mg times r. Okay, or weight times that radius. And so the condition for escape, the velocity for escape, is actually mgr times 2. Take the square root of that. And that's going to be divided by m because there's an m on both sides. So it's just v escape is equal to the square root of 2 times g times r. All right. All right. And so at that point, you can solve for the escape velocity. Times that radius, which we decided was 6.67 times 10 to the 6th. Okay. Still don't like this problem, but, well, we're here. We might as well finish it off, right? And Logan's insight is actually validates moving forward. And that number turns out to be 11179.4. And that would be this is in meters squared per second squared. So meters squared per second squared inside of the radicand. So that's going to be meters per second. Or since it's quite a large number, we could write that as 11.2 kilometers per second. Okay. And so that's going to be your escape velocity. Okay. All right, so you guys have any questions? It's kind of a messy execution. I'm not really crazy about this problem. I thought I would like it a lot better than I did when I started it, so. Right. Well, I guess that'll do, though. We don't really have to work another problem because it is exemplary enough that I think it will step you through that thing. Let's take a look at this. This is just so messy to me. It's okay. Yeah, let's just leave it alone. All right, so that is it for today. Those are 2 problems that will get you started with your homework. Don't hesitate to come see me, and we will not cover any new material this weekend, and we will not have any more homework this weekend. So get started on problem sets 1 and 2, and then on Monday we'll talk about section 13.3. So you guys have a great weekend.